Shor's quantum algorithm explained quantum algorithms represent a revolutionary shift in computation, leveraging the peculiarities of quantum mechanics to solve problems deemed intractable by classical systems. Among these, Peter Shor's groundbreaking algorithm stands out as a landmark achievement, capable of factoring large numbers exponentially faster than traditional methods. This article delves deep into the intricacies of Shor's algorithm, exploring its origins, underlying principles, and profound implications for fields ranging from cryptography to computational mathematics. Whether you're a programmer seeking to grasp the fundamentals or a researcher interested in advanced implementations, this guide offers actionable insights into quantum problem solving. The genesis of quantum algorithms in the early 1980s, Richard Feynman proposed that simulating quantum systems classically was inherently inefficient due to the exponential growth of possible states. This insight laid the groundwork for quantum algorithms designed to exploit parallelism and interference phenomena unique to quantum physics. Peter Shor's 1994 paper introduced his eponymous algorithm, demonstrating how quantum mechanics could factorize integers in polynomial time, a feat unattainable by known classical approaches. This revelation sent shockwaves through the field of computer science and cybersecurity, sparking urgent efforts to develop post-quantum cryptographic protocols. Feynman's hypothesis, classical simulation of quantum behavior is fundamentally limited by resource constraints. Shor's breakthrough, factoring becomes feasible in O log n, 3 time, threatening RSA encryption's foundation. Classical versus quantum computation fundamentals. Traditional computers operate using binary digits, bits, represented as zeros or ones. These bits exist in definite states, processing information sequentially through logical gates. In contrast, quantum computers utilize qubits, which leverage superposition and entanglement to perform parallel computations. A single qubit can exist in a superposition of a 0 and 1 simultaneously, allowing quantum circuits to explore multiple solutions concurrently. When combined with entanglement, the phenomenon where particles become correlated regardless of distance, this enables complex operations impossible for classical systems. Superposition permits quantum states to represent vast combinations of values, while entanglement allows instantaneous correlations across separated qubits. Together, these properties form the backbone of powerful algorithms like Shor's. Measurement collapses a quantum state into a classical outcome, probabilistically selecting one result among many possibilities. This collapse introduces randomness but also provides mechanisms for amplifying correct answers through constructive interference. Diving into Shor's algorithm mechanics at its core, Shor's algorithm solves integer factorization by reducing the problem to finding the periodicity of a function related to modular arithmetic. This involves three primary stages: pre-processing, quantum computation, and classical post-processing. The algorithm begins by selecting a random number, a coprime, to the target number n. It then constructs a function f, x, equals a to the power of x mod n and determines its period r, which reveals factors of n if r is even and a caret, r/2, is not equal to plus or minus 1 mod n. Implementing this requires creating a quantum circuit with a register for input states and another for output measurements. Applying Hadamard gates generates superpositions, and the quantum Fourier transform identifies periods hidden in probability distributions. The success hinges on accurately determining the period r, which depends on the size of the quantum register and precision of the Fourier transform. Errors here necessitate rerunning the algorithm until reliable results emerge. Breaking down key components of Shor's algorithm: modular exponentiation. A crucial component computes a to the power of x mod n efficiently using repeated squaring techniques adapted for quantum circuits. This operation remains computationally intensive yet manageable within the framework of quantum parallelism. Period finding identifies cycles in functions defined over finite groups. For Shor's purposes, this translates to locating repeating patterns in sequences generated by modular exponentials, enabling extraction of prime factors. Quantum Fourier transform QFT converts a wave function representing probabilities into frequency domain data, making visible the periodic nature embedded in the quantum state. QFT operates in O(n superscript 2) time, significantly faster than classical FFT equivalents. Error correction mitigates noise-induced errors inherent in physical qubits. Techniques like surface codes or topological qubits help stabilize computations, although current implementations remain imperfect due to technological limitations. Comparative analysis with classical methods. Classical algorithms for integer factorization include trial division, Pollard's row method, and the number field sieve, NFS. While NFS holds records for largest factors found, its runtime grows sub-exponentially, becoming impractical for sufficiently large primes. Shor's algorithm achieves polynomial time complexity, O log n, 3, versus exponential growth seen in classical counterparts. This makes it theoretically viable for cracking RSA keys once scalable fault-tolerant quantum computers materialize. Cryptography impact. The threat posed by Shor's algorithm motivates ongoing development of lattice-based or hash-based cryptosystems resilient to quantum attacks. Governments and organizations actively invest in transitioning infrastructure away from vulnerable standards. Practical limitations. Despite theoretical advantages, current noisy intermediate-scale quantum devices lack the qubit counts and coherence times needed to execute full instances of Shor's algorithm meaningfully. Research focuses on optimizing error rates and increasing system stability. Applications beyond integer factorization. While Shor's algorithm gained prominence for its impact on public key cryptography, researchers continue expanding quantum algorithm toolkits to tackle diverse challenges. Notably, Grover's search algorithm demonstrates quadratic speedups for unstructured databases, applicable wherever brute force enumeration dominates performance bottlenecks. Other promising avenues include solving linear equations via Haro-Hassidim-Lloyd (HHL) algorithm, accelerating chemical simulations through variational quantum eigensolvers (VQE), and enhancing optimization tasks with adiabatic or gate model approaches. Economic and industrial implications. Industries relying heavily on combinatorial optimizations, from logistics planning to financial risk modeling, stand to benefit immensely from efficient quantum solvers. Early adopters may gain competitive edges by integrating prototype solutions now emerging from academic labs. Pharmaceutical companies explore quantum-enhanced drug discovery pipelines, aiming to simulate molecular interactions at unprecedented speeds. Such capabilities could drastically reduce timelines for bringing novel compounds to market. Challenges hindering widespread adoption. Despite theoretical promise, scaling quantum computers faces formidable obstacles. Maintaining qubit coherence amidst environmental disturbances remains a persistent challenge requiring innovations in materials science and control engineering. Current architectures suffer from high error rates and limited connectivity between qubits. Overcoming these demands robust error correction schemes, often demanding thousands of physical qubits to implement a single logical qubit reliably. Decoherence times. Interactions with surrounding environments cause rapid loss of quantum information. Researchers strive to extend these durations through cryogenic cooling, electromagnetic shielding, and specialized fabrication processes. Noise reduction. Implementing precise gate operations amid thermal fluctuations and crosstalk presents significant hurdles. Advances in microwave pulse shaping and dynamic decoupling offer partial mitigation strategies currently under investigation. Recent advancements and future prospects. Ongoing research aims to enhance algorithm efficiency and hardware reliability. Innovations in photonic qubits, trapped ions, and topological qubits suggest varied paths toward achieving scalable quantum processors suitable for running sophisticated algorithms like Shor's. Hybrid models combining classical and quantum components show promise for addressing near-term limitations. These architectures enable tackling portions of problems with existing quantum systems while delegating others to classical cores until larger-scale machines arrive. Algorithmic improvements. Work continues refining versions of Shor's algorithm suited for noisy intermediate-scale quantum (NESQ) devices, focusing on minimizing resource requirements while preserving essential functionality. Education and community engagement. Initiatives promoting open-source frameworks facilitate experimentation with quantum software stacks. Platforms like Qiskit and Project Q allow developers worldwide to contribute to advancing knowledge through collaborative projects. Conclusion: understanding quantum algorithms represents a pivotal step for programmers and researchers navigating tomorrow's computational landscape. Shor's algorithm exemplifies how exploiting quantum phenomena opens doors previously thought inaccessible by classical means. As we approach eras dominated by hybrid and fully quantum systems, staying informed about evolving paradigms ensures readiness to harness transformative technologies reshaping industries globally. Embrace the journey into quantum computing. It promises unparalleled opportunities awaiting exploration.